Angular velocity of a pendulum. A pendulum in the shape of a rod is released from rest at an angle of 30 degrees. It has a length of 30 centimeters and mass 300 grams. What is its angular velocity at its lowest point? This is based on the rotational motion, and then the problem can be solved taking the conservation of energy. Here the rod is swinging like a pendulum. Okay. So this is the pivot point, and then this is the extreme position, and this is the lowest position, or this is the equilibrium position. Now, the pendulum is making an angle of 30 degrees with the vertical. When the pendulum is at its extreme position, it has only gravitational potential energy. When it is at the equilibrium position or the lowest position, it has the rotational kinetic energy. Now the question is to find out the angular velocity. To find out the angular velocity, we have to equate the energies. Okay, the total energy of the system is conserved. Therefore, the gravitational potential energy at the extreme position is equal to the rotational kinetic energy at the lowest point. Now write down mgh is equal to half I omega square, or ug is equal to delta k, or delta u plus delta k is equal to 0. Okay, or delta E is equal to 0. That means the total energy of the system remains constant. Or here we are taking the gravitational potential energy and rotational kinetic energy. Therefore, the total energy of the system remains constant. And we know the rotational kinetic energy is equal to half I omega square. No problem in that. And then gravitational potential energy is equal to mgh. Now, how to find out h? Here, we have to find out, see here, this is the h. This is the lowest point and this is this one. So, this difference is the h. Even if here, you can see, this is the h. Okay. So, this length is h. Okay. So this one, suppose if I draw like this one. So this is the h. Okay. Now this h we have to find out. So when the we have to, because this is the rotational motion, the distribution of mass takes an important role in the rotational motion. Okay. Here the rod is a uniform rod. Okay. Therefore, the center of mass lies at the center of the rod. So the length of the rod is L. So at L by 2, we have the center of mass located. What is center of mass? Center of mass is the point where the entire mass of the object appears to be concentrated. Okay. So for this rod, uniform rod, the center of the location of the center of mass is the midpoint of the rod. Okay. Now we have to find out where is the what is the height h of the center of mass. Okay. So for that here you see this one. So this is the L by 2 and then h center of mass. H center of mass, I have drawn the right angle triangle here. Okay. Same thing, right angle triangle. So this vertical line is HCM, that means the center of mass, and this is L by 2. So the center of mass is located at L by 2. No? So it has made a height of h. Suppose if it is at the normal position, it will be h. Okay. L by 2. Okay. Now, cos theta is equal to adjacent side by hypotenuse. Am I right? So, therefore, cos theta is equal to h center of mass divided by L by 2, or h center of mass is equal to L by 2 cos theta. Okay. So, energy at the extreme position is equal to energy at the equilibrium position. Therefore, E top is equal to E bottom. E top is equal to, here, it will be mg L by 2. Here L by 2 is mg HCM, this is mg HCM is equal to mg L by 2. Here it has no rotational kinetic energy. Therefore, mg L by 2 cos theta plus 0 is equal to, at this position, the center of mass is again at a height of L by 2 from the lowest point. So, therefore, mg L by 2 at the lowest point, or at the equilibrium position, the height of the center of mass is mg L by 2. And then the rotational kinetic energy is equal to half I omega square. Here the negative sign indicates that the direction, it is the rod is moving in the clockwise direction, therefore minus half I omega square. Now solve for omega square. Just rewrite the equation and then solve. You will get mgl by 2 times 1 minus cos theta is equal to half I omega square, and I is equal to 1/3 ml square, and substitute the values, and then you will get the omega as 3.62 radians per second. This is one of the methods to solve the problem. There is one more method I will teach you. Now see this one. So this is the center of mass. This center of mass is at this point. This the center of mass is located at L by 2 and it is at a height of h. Okay. And therefore take the right angle triangle. This will become L by 2 minus h, and then the hypotenuse will be L by 2. Therefore cos theta is equal to L by 2 minus h divided by L by 2, or L by 2 cos theta is equal to L by 2 minus h, or h is equal to L by 2 times 1 minus cos theta. Okay. Now, what we are doing here, E initial is equal to E final. E initial is gravitational potential energy. Gravitational potential energy is equal to mgh. So instead of h, I am writing L by 2 times 1 minus cos theta in the equation mgh. Okay. And that is equal to half I omega square. Again, I is equal to 1/3 ml square. And then the values we can substitute, and we get omega is equal to square root of 13.122, or omega is equal to 3.62 radians per second. Okay, so these are the two different ways to solve the problem. One is directly substituting EA is equal to EF, and then considering the center of mass as at the height of L by 2, and then solving for H, and then finding out omega. Another one is this one. At the extreme position, we have only the gravitational potential energy. At the lowest point, we have both the gravitational potential energy and rotational kinetic energy, because the center of mass is located at a height of L by 2 from the lowest point or from the pivot. You can consider anything. Okay. And then substituting the value, you will get the answer. Just this is a conservation of energy, nothing beyond that. Hope this helps. Thank you. Bye bye.